Welcome to The Explainer. Today, we're diving into a really fascinating paradox that sits right at the very foundation of computer science. We're going to look at an algorithm that's pretty much a rite of passage. It's taught to almost every first-year programming student, and the core idea is so incredibly elegant that you can grasp it in seconds. Yet, and here's the crazy part, it's an algorithm that has historically brought even the absolute most brilliant programmers to their knees. We are, of course, talking about the deceptively simple binary search. To really understand the stakes of what we're dealing with today, we should listen to the legendary computer scientist Donald Knuth. He actually hit the nail on the head when he wrote, "Although the basic idea of binary search is comparatively straightforward, the details can be surprisingly tricky." And he wasn't kidding. Knuth pointed out this absolutely staggering piece of computing history. Binary search was first published in 1946, right? Well, the very first published version that was actually entirely free of bugs didn't show up until 1962. I mean, think about that. That is 16 years of literal geniuses publishing flawed code for what is supposedly a basic algorithm.
Now, what's really interesting about this slide is that the number 10 isn't just some random figure. It represents the exact number of years that a massive, fundamental bug sat entirely undiscovered in the binary search implementation of Java's standard library. Yep, for a full decade, developers all over the world trusted this core piece of code, completely unaware that under certain conditions, the whole thing would just critically fail. We're definitely going to reveal exactly what that sneaky bug was a bit later in this explainer, but first, we need to make sure we're on the same page about how binary search actually works in practice.
So at its core, the main mechanic here is just having the search space. Instead of checking a sorted list one boring item at a time, you just jump straight into the middle. You grab that middle item and compare it to your target. If your target is smaller, boom, you instantly know it has to be in the first half of the list. If it's larger, it's in the second half. That one single comparison instantly discards half the possibilities. It aggressively, ruthlessly shrinks the problem down. And then, you just repeat that exact process on the remaining half over and over until you find your target.
When you translate that elegant idea into actual logic, you get something like this pseudocode for a recursive binary search. If you look at the meat of it, lines 11 through 18, the code calculates the midpoint, calls it m, and makes that crucial comparison. If your target x is less than the midpoint, the algorithm literally calls itself again, but only on that first half of the array. If it's greater, it recurses on the right half. It's just this beautiful, continuous loop of self-reference that whittles a massive search down to a mere fraction in no time.
Which naturally brings us to the absolutely crucial question of speed. In computer science, we measure this using time complexity, which we usually denote as T of n. Basically, this is just the maximum number of comparisons an algorithm needs to make on a list of n elements. Now, because we're slicing the search space in half with every single step, our worst-case scenario forms a very specific mathematical boundary. Basically, for any list of size 2 or bigger, the time it takes is, at most, one single comparison plus whatever time it takes to search half the list.
Okay, to make this math feel a bit less abstract, our source material offers this fantastic, vivid metaphor called the kitty smashing method. Imagine your data is a physical ball of size n. In one step of our algorithm, we take that ball and we shatter it into a smaller ball exactly half its size. Every time we do this smash, we pay a cost of 1 unit, and we drop that unit into a collection jar, the kitty. We just keep shattering the ball, cutting its size in half, paying our 1 unit, until the ball is whittled all the way down to a size of 1. So, if you start with a ball of size 23, it shatters to 11, then 5, then 2, then 1. That's just 4 smashes. Mathematically, this translates perfectly to the base 2 logarithm. The number of operations grows so incredibly slowly, which is exactly why binary search is astonishingly fast, even when you're dealing with massive datasets.
Let's zoom out for a second and see how this all fits into the bigger picture of computer science. Binary search is traditionally held up as this shining, classic example of the divide-and-conquer paradigm. The basic philosophy here is that instead of tackling a giant, overwhelming problem head-on, you decompose it. You break it down into 2 or more similar but much simpler subproblems. You solve those tiny chunks, and then you compose those solutions back together to solve the big one. It's quite literally a foundational architecture of thought that powers modern computing.
And this paradigm, it has deep, deep historical roots. The whole idea of using sorted lists to make searching easier actually dates all the way back to Babylonia around 200 BC.
Fast forward a few centuries to 1805, and you have Carl Friedrich Gauss using a very similar approach to develop what we now know as the fast Fourier transform. That incredible breakthrough paved the way for computing pioneer John von Neumann to invent the merge-sort algorithm in 1945, using a two-subproblem divide-and-conquer approach. And ultimately, this all leads us to 1960, when mathematician Anatoly Karatsuba totally shocked the math world by applying this exact same logic to multiplying massive numbers together.
Just to put into perspective how much of a game changer this was, look at the difference Karatsuba's approach made. The standard classroom method we all learn for multiplying two n-digit numbers, it requires n-squared operations. Like it's really slow, really fast. But Karatsuba realized that by breaking those large numbers into halves and recursively multiplying the smaller parts, you could drop the total operations to n to the power of log base 2 of 3, which is roughly n to the 1.58. Now that might sound like a tiny tweak, but as numbers get huge, that slight change in the exponent causes an absolutely unbelievable speedup. It proved once and for all that intelligently dividing a problem can fundamentally rewrite the computational limits of what we think is possible.
Now, while academia is generally pretty comfortable just dropping binary search straight into the divide and conquer bucket, if you go to programming communities like Reddit or Stack Overflow, you'll find a really passionate, highly technical debate going on over this exact label. The big question that constantly gets argued is this: is binary search actually a true example of divide and conquer? On one hand, you have iconic standard textbooks like the ones by Skeena or Kleinberg, and they lump binary search right in there alongside merge sort in their divide and conquer chapters. The logic is simple. You are dividing the search space, so it counts. But a lot of seasoned programmers in the trenches fiercely push back against this.
These critics point to a very, very specific distinction. They argue that true divide and conquer, like merge sort, breaks a problem into multiple subproblems, solves them all, and then has a critical conquer step where it actually combines those solutions back together. Binary search, on the other hand, it just takes the list, entirely discards half of it, and leaves you with one single smaller subproblem. There is absolutely no combination step at the end. Once you find your target, boom, you're done. Because of this missing step, many purists argue it shouldn't be called divide and conquer at all, but rather decrease and conquer. It's honestly a fascinating little window into how much exact semantics matter in the computer science community.
Okay, let's dive right back into our original mystery. Because whether you're team divide or team decrease, the core logic is still incredibly straightforward. So why do brilliant programmers constantly mess it up? Why is it that developers write completely buggy binary searches when the concept itself is basically child's play?
Well, there was this researcher named Richard Pattis who actually analyzed 20 different computer science textbooks. We're talking the exact books used to teach the next generation of coders. And he found that out of 20 books, only 5 of them had implemented a correct binary search. 5, the rest were completely littered with logical errors. Programmers forget to handle what happens when the list is empty and the size is 0. They make classic off-by-1 errors when setting up the next interval, which traps the program in an infinite loop. They totally fumble how to handle duplicate items, returning the wrong index, or worse, they accidentally tell the program to access memory completely outside the bounds of the array. It seems like the algorithm's simplicity actually creates this false sense of security, you know? People just throw the code together without respecting the strict logical boundaries.
But out of all those mistakes, the absolute most notorious trap, the exact one that plagued Java for a full decade, lies right in calculating the midpoint. Your natural instinct is probably just to take the starting index, add the ending index, and divide by 2, right? It makes perfect mathematical sense. But here's the massive trap. If your array is gigantic, say 1 billion items, adding those two indices together creates a number so large that it actually exceeds the maximum value a standard integer variable can hold in computer memory. This triggers what's called an integer overflow. The number literally wraps around to a negative value and instantly crashes your program. It went completely unnoticed in Java for 10 years simply because, for a long time, nobody was really searching arrays quite that massive. The elegant, completely bulletproof solution? You just subtract the start from the end, divide that by 2, and then add it back to the start. It gives you the exact same midpoint mathematically, but completely bypasses the danger of overflowing your memory.
It's honestly a pretty humbling reality check. A completely routine mathematical calculation, literally just finding an average, managed to break one of the most widely used programming languages on the planet, all because of the invisible physical constraints of memory. And I think it leaves us with a genuinely provocative question. If an algorithm as thoroughly studied, beautifully elegant, and conceptually simple as binary search can harbor a critical, show-stopping bug in a major library for 10 whole years, how many other simple algorithms, hidden deep inside the phones and laptops we rely on every single day, are quietly harboring undiscovered flaws, just waiting for the exact right conditions to blow up? It's definitely something to keep in the back of your mind the next time you sit down to write a simple piece of code. Thanks for joining me on this explainer, and keep exploring.